which is known as current IT, and we are going to derive the current through the MOSFET transistor using the charge voltage condition for the MOSFET device. Okay. So just for clarity, let us assume that in this two-dimensional plane, this is our y direction in the length of the channel. The channel length will start from here, so y equal to 0 here, y equal to maximum L when you reach at the top of the channel. So the channel length is from the distance from the source to the drain. So if I assume that this is my y direction and y is in the direction of the channel length, y will be 0 at the source end, y will be equal to capital L, the length of the channel. So anywhere it will be a function of y, the length, and the voltage will be function of y, Vy. So now, along the channel, we have a gate channel capacitance effective across the gate and the channel, right? That's what we have discussed. That this gate channel capacitance will appear again and again. So across the channel, there is a gate channel capacitance, COX times W times L. COX is the per unit area capacitance across the gate to channel. That's the technology parameter. So now, along the channel length, the total charge, the charge Q, we know that charge Q is equal to CV. That's the general definition of charge. Charge is equal to capacitance times effective voltage across that channel. Now, how much effective voltage across the channel there is there? Vertically, we have applied VGS. Horizontally, along the channel, we applied VDS. So, these two resultant voltage, VGS minus VDS, of course we have to subtract the VT. This is the total effective voltage across any point in the pool. Now, this one, VDS, it starts from, let's say this is y equal to 0 channel. It is 0 at this end. It is full strength VDS at the drain end. So this is a variable. We don't know yet. So now, but together VGS minus VDS, typically we call it VGC. Total applied effective voltage will gain across the gate channel region. This is we applied vertically, this is applied horizontally. So the difference between these two voltages is gate channel effective voltage. We have to always subtract VT because up to VT there will be no channel. So this is the general expression for effective voltage across the channel, VGC minus VT. But I immediately split VGC. VGC is VGS minus V of Y. V of Y is the variable voltage across the drain channel. Y equal to 0 here, Y equal to L here. VDS, Vy is actually VDS, it is 0 here, it is maximum VDS here because it is applied in the length, in the direction of the channel. So at any given point, arbitrary point along the channel, the charge Q of Y equal to COX, the gate channel capacitance per unit area, times effective voltage, which is VGC minus VT. But in this particular slide, let's start with an NMOS transistor. When we are talking about NMOS transistor, the charge that we have accumulated in the channel is a negative charge. So the charge then instead of Qy, I would write Qn of y to indicate that we are talking about a negative charge, electron charge. So there will be a negative sign here because the amount of charge that we have accumulated, it is a negative charge. Times COX, and what is VGC? VGC is the effective voltage due to gate voltage and the drain voltage. Gate voltage is always fixed at supply, VGS, minus V of y, which is variable along the channel length depending on where you are fixing the y, minus Vt. So Qn of y, the negative charge accumulated in the n-type channel will be equal to minus COX times the effective voltage difference. So that is the total charge per unit area along the channel. Why you are calculating this charge? Because, yes.
VGC, it's gate channel voltage, right?
Yeah, total effective voltage across the channel. Yeah. So it's a resultant of VGS and variable voltage VDS or VY. Now, while you are calculating, why you are so interested in calculating accurate amplitude and the polarity of the current, because the charge, because current I is equal to what? Flow of charge per unit time, right? Current I equal to charge over time. Coulomb over second is ampere. So, if we know the charge that is accumulated or flowing through the channel, we can calculate the current. Now, current, what current we are talking about? The current that is electron flow that is going out of the channel, out of the drain, that is current that is entering into the drain. When electron flow in this direction, current is in the opposite direction. So current ID is total, the Q divided by T. Now, in the previous slide, this charge we expressed in terms of COX. COX is gate channel capacitance per unit area. However, the total charge across the gate channel will be, I have to multiply it by area of the channel. Area of the channel is length of the channel times width of the device or width of the channel, right? So COX is the per unit area capacitance in the channel region times the total area of the channel overlap, that is the total charge. So the current is total charge divided by T. So now, so total charge Q is W times L, that is the total area of the channel, times Qn of Y, because we are talking about NMOS transistor. So we replace the value of Qn. Qn is here minus COX, its whole expression. We just replaced it here. So that is my total charge. Now, I got the total charge expression. Now the question is, how much time an electron will take to travel from source to the drain end? So if I want to move Q amount of charge from here to here, and then I can calculate the time for an electron or certain amount of charge to move from here to here. If I then calculate that time, then charge divided by time is my current. So how do we calculate the time? Here, the channel length, this is my channel, the channel length is L. If the electron velocity along the channel is V, so the time T will be L over V, right? Distance over velocity, simple linear calculation. So the now question is, how do we calculate velocity of electron? So diving deep into physics, so length over V. Now how do we calculate velocity of electron? Velocity of electron through any medium is dependent on its electrical property, mobility, and the applied electrical field. If we apply more force, more electric field, then it will move at higher velocity. If you apply less electrical field, it will move at less. So velocity of any electronic particle, electron and hole, is equal to its mobility times electrical field. If we are talking about electron, it will be mu n. If we are talking about a hole, it will be mu p. So velocity of v is mu n times e. So now we got all the expressions. So we got id equal to q divided by t. We got the total value of q. We got the t and velocity v. Now, if I put this t into v, v into t and q into id of t, what we get? So therefore, the current that can be given by id equal to minus w times qm of y times mu and e. So L and L will cancel each other, right? L and L will cancel each other. So from this expression, here L. So now instead of V, I wrote mu and V here. Now the question is, so now Qn I can replace with the whole expression. So in this expression of ID, so this is a general expression of ID, current ID through an NMOS transistor. This is NMOS transistor, is mu n. So through an NMOS transistor. In this expression, what are the things that we know and what are the things we do not know? W is the width of the transistor. It's a geometric constant. COX is the per unit area capacitance of a certain technology generation transistor that you can read from technology information or data sheet. VGS, we always apply highest possible gate voltage that is equal to supply. VT is the threshold voltage for a certain transistor in a technology generation. There is a constant for that technology that we know. Mu n, electron mobility in a certain electrical field medium or material, is constant. E is the electrical field, we don't know. V of y is the variable depending on where you are setting the y, at the beginning or at the end. So these are the two variables. We have to find a way to replace this E because we don't know exactly electrical field, and we have to solve it for certain y. Yes.
Isn't the electrical field is constant?
It depends on where you are calculating the electrical field. Ultimately, if we apply total supply here and here, it will become constant. So, but before we reach to that point, now we are talking about along the channel in terms of y, so we are not even mentioning whether it's constant or not. But at this point, before even analyzing that, this is a constant, this is a constant, this is constant, this is a constant, this is a constant. 1, 2, 3, 4, 5 constant, and then these two here we have to analyze. So now, so this is our general expression of current ID. Now we are going to apply it to these three regions: cutoff region, linear region, and saturation region. What is the current? For cutoff region, when the gate voltage, when the cutoff, in the cutoff region, when the gate voltage please ask question if you cannot follow me. If the gate voltage is threshold voltage, right? In the cutoff region, this is the cutoff region, current ID will be 0. Why? Because in the cutoff region, there is no electrical field applied, there is no channel formed, so current ID is by default 0, so you don't have to worry. But what happens in the linear region? In the linear region is when gate voltage is positive, but drain voltage is positive, but it is below the threshold voltage. At and above threshold voltage, it will enter into saturation. So we are going to apply, so cutoff we don't do derive, we know is ID, ideally ID is 0. we are going to apply that saturation condition here to get one unique expression for linear region and another unique expression for saturation region. So, in the drain current in the linear region, now let's say that VGS is initially, why we call it linear region? Because initially, gate voltage you all know that it is equal to supply. Drain voltage we are increasing. We are increasing from 0 and above. So initially, current will linearly increase with the increase of the drain voltage. It acts like a resistor, so it's called linear region of operation. How long that linear region of operation will continue? Until a pinch off occurs. That's when saturation starts. Pinch off occurs when this condition happens, when at the tip of the channel total effective voltage becomes 0. So now at the tip of the channel, when first the charge becomes 0, this condition satisfied, what would be the value of Y? L, because L, the Y channel, this is Y equal to 0, this is Y equal to L at the end of the channel, right? So VDS is applied here, so pinch off will start here. So which point we'll see the pinch off starting? When Y equal to L. At that point, the total effective voltage is VDS. So when VGS minus VDS minus VT becomes equal to 0, right? That means when VDS becomes equal to VGS minus VT, that's where device enters into saturation. Up until that point, when drain voltage is less than this threshold voltage, the current is in linear region of operation. So that observation we are going to utilize to calculate the current in the linear region. So now ID is general expression we know. So now electrical field, I am introducing lots of basic definition here. Which side is more visible, this one or that side? So electrical field, E is what? Voltage divided by distance, right? Or length. Volt per meter is the electrical field. So in this particular case for NMOS transistor or PMOS, any MOSFET transistor, electrical field in the direction of the channel Y will be what? dV over dy, because Y is in the direction of the channel and is the length equal to 0 in the source end, this Y is equal to L in the drain end. So electrical field is dV over dy per unit area voltage applied is electrical field. Now I want to replace that E from this expression. So now in this particular case we are here deriving the current equation for NMOS transistor. For an NMOS transistor, the applied, if electrons are moving in this direction, I am applying electrical field in this direction, electron is flowing in this direction, the assumed direction of the current is opposite. So it's a negative field. In case of positive particle, in the direction positive particles are moving, current direction is assumed in the same direction. But in case of electron, if electron moves in this direction, positive direction of the electron is in the opposite direction, right? So this electrical field in this particular NMOS case, it will be minus dV over dy because electrons are moving in the opposite direction, because we are talking about electrical field effective in an N-type channel, NMOS transistor, right? So it will be minus dV over dy because current flow and electrical field, they are in opposite direction. So initially we had a minus at the beginning of ID. Now E is replaced by minus dV over dy. That minus and initial minus cancels each other, right? So ID is mu n Cux W is dV over dy. So now we replaced E. Initially in the previous slide we didn't know what is E. Now we replaced E. Now in this equation mu is a constant, Cux is a constant, W is a constant, Vgs is equal to supply, V and Y is a constant, Vt is a constant, and the whole function is a function of Y, right? So now for algebraic manipulation, this dy, let's put this here, and this side is variable of t, this side is variable of y, right? Yes.
Vy, you said it's a variable, right?
Yeah, Vy is a variable.
So how did it become constant?
It didn't. It still is a variable because it's V of y. It is actually
The length, the
around
voltage,
the length of the
around the length of the
effective
voltage,
drain
drain voltage.
depending on where you are setting the y. If we do it at the beginning of the channel, y equal to 0.
Zero.
If at the end, y equal to L. So now we are going to calculate the total current coming out of the drain terminal or entering into the drain terminal, right? So to replace the variable, what do we have to do? We have to take the total limit of y, which is y equal to 0 to L, and total limit of v of y. V of y limit is what? At the beginning it is 0. At the end, v of y is equal to full voltage VDS, right? So the limit of v of y is at the beginning 0, at y equal to 0, is equal to total drain voltage when y equal to L, right? So this side, if I integrate from 0 to L, this side I integrate from 0 to VDS. I intentionally skipped few lines here, assuming that you know the basic integration. So if I integrate this one from 0 to L, if I integrate this side from 0 to VDS, all these are constant. This is the final expression I get. ID is equal to mu and Cux times W over L times VGS minus VT times VDS minus VD squared divided by 2. This is the final expression. So this is one of the most popular current equation for ideal behavior analysis of any MOSFET transistor. That's why it is called ideal IV characteristics of MOSFET for linear region. This equation tells us how a transistor will behave for a certain applied voltage. Its current and voltage relation. For any transistors, there are two voltages we apply, gate voltage and the drain voltage. With respect to those gate and drain voltage, for certain drain and certain gate voltage, how much current you can get, this relation will tell us how much current you get in the linear region of operation. Now the question is, when the word linear comes to your mind, the relation should be linear. But if you look at this, yes, this side is completely linear. But there is a fraction here, there is a term here, which is square, quadratic relation. But the thing is, at the beginning of, so when is the linear region of the transistor occurs? When VDS, when you apply a gate voltage, you turn on the transistor, VDS is still 0, you are gradually increasing it. So initially VDS is very small. It's fractional, let's say a fractional value. So square of a fraction is even smaller value, right? So initially when drain voltage is much smaller, slightly above 0, below saturation, this term will be a much smaller term compared to this term. That's why this linear term will dominate the behavior of MOSFET, so we can say that it is still in linear. But as you reach closer towards saturation voltage, the linearity will no longer hold. What will happen? Let's say this is you are increasing VDS here, and this is current ID. Initially, with the increase of VDS, it will gradually increase, but then it will slowly increase up to saturation. And then from saturation, it will become constant. So initially, it will be truly linear because VDS squared divided by these two terms will be very, very small. But as you increase VDS, this term will become larger and larger, so it will not be truly linear anymore, so it will gradually saturate. So saturation will not take place instantaneously. Initially it will be sharply linear, and then gradually it will saturate, and at one point, when VDS reaches its saturation voltage, it will become constant. So now, this is the ideal current equation. So one of the two most frequently used equation to analyze the behavior of MOSFET. The actual behavior will be significantly different from this because this is called a second degree model. So any one of you use SPICE simulation or any circuit simulation? So whenever you use a circuit simulation, behind the scene, it solves millions of equations like this. So if you want to calculate ID current, the drain current from a simple MOSFET device, even the simplest version of SPICE will utilize an equation significantly more complex than this. So let's say if you are, because it will add all the non-idealities and other parasitics and factors. If you are doing a simulation for IBM or Intel, probably they will be using a level 64 model in commercial version. Level 64 means there will be a term to the power 64. So in probably those type of like commercial SPICE models, you cannot run using a regular PC, and even those powerful PCs, sometimes it takes 2-3 days to complete a full-scale simulation. So that's a different story. Now let us see what would be the current in the saturation region. Yes?
Do we need to derive this equation?
No. I'm just showing you step by step why this one is called linear, but you are going to use this equation frequently in the next 3 lectures to solve all of your problems.
Okay.
So you don't have to memorize this equation, it will come in the exam sheet as a cheat sheet, but it is important to understand this dependency. Now let us see what is the drain current or diode current in the saturation region. Saturation region starts when VGS minus VDS minus VT becomes equal to 0, or VDS becomes equal to drain saturation voltage, which is VGS minus VT. Before that, it is in linear region. So now, if the device enters into saturation, then VDS is called VD set, and it is equal to VGS minus VT. So I am just replacing value of VD set into the previous equation we just derived. So now VD set is equal to what? VGS minus VT. So this term is equal to VGS minus VT whole square. This is VGS minus VT whole square divided by 2. As if it is x square minus x square divided by 2, right? So it will be, the total resultant will be VGS minus VT square divided by 2. So now current ID in saturation region is equal to mu n Cux W over L times VGS minus VT square divided by 2. So this is called very famous IV characteristics of MOSFET transistor in saturation region. Now, what is the definition of saturation region? In saturation region, if you further increase the drain voltage, the current will no longer increase. That means current becomes insensitive or independent of the drain voltage. So, now if you look at this equation itself, in the final expression of current in the saturation region, there is no term containing VDS. So that shows that you increase or decrease VDS beyond saturation, current will not have any impact. If you increase the gate voltage, it will increase quadratically. But if you increase or decrease drain voltage in the saturation region, current will not change. So that shows that it has become independent, saturated. So these two equations side by side written as a pair of equation, current ID in the linear region and current ID in the saturation region. So now if we want to summarize again those three regions of NMOS transistor operation, in the cutoff region, when gate voltage is less than equal to threshold voltage, MOSFET transistor is off. So the current ID will be equal to 0. When the gate voltage is above threshold voltage, transistor is on, but the drain voltage is still below the saturation voltage. The MOSFET is in on, but it is in linear region, and its current ID will be given by this expression. And pinch off region occurs when drain voltage becomes equal to saturation voltage. From that point onward, that device enters into saturation when gate voltage is above threshold voltage, drain voltage is equal to or greater than saturation voltage, and in that saturation region, current ID is given by this. So now, if you want to write these four set of conditions for NMOS transistor, what do you have to do?
It's the opposite.
You just become GS become SG, DS become ST. Because in case of NMOS transistor, source terminal is the lowest terminal. Every voltage is measured with respect to source. Source is connected to ground. So gate is above, drain is above, everything. So ground connection, ground and body, they are tied together and they are connected to source. In case of PMOS is opposite, because at the gate terminal you need a negative voltage, at the drain terminal you need a negative voltage to pull the holes out, positive holes out. So source has to be at the higher reference point supply. Gate and the drain has to be at the lower potential. So I have to write, instead of VSG, I have to write
VGS.
GS. So instead of VGS, it is saying that it's higher potential. Second one is the lower potential. For PMOS, we have to write VSG. For
VSG.
we have to write VSG.
VSD.
Now what will happen to threshold voltage? Threshold voltage is a negative, but we want the difference between gate voltage and the threshold voltage. So in case of PMOS, we always write magnitude of threshold voltage, not the actual value. Magnitude. So that's why in literature you will see that VTN is written for NMOS threshold voltage, and VTP inside the equation will always written as a magnitude because it's actually a negative quantity. So if you want to write all these three equations, condition for PMOS. So let me write here. Let me see. Do I have a slide on this? Yeah, this is the one we are talking about, but we will explain that. But now let us look at graphically what we have derived so far. Current ID for linear region, current ID for saturation region. As I mentioned over there, as you can see, for a certain gate voltage, let's say the circuit you are working with has a 1 volt supply. So gate voltage will be exactly equal to 1 volt because we want to turn the transistor very strongly on. So for a 1 volt supply, gate voltage will be 1 volt. Drain voltage VDS, as I am increasing, initially it will linearly increase, but gradually it will slow down, and this dotted curve is showing the saturation. When drain current reaches its saturation, from then it becomes constant. So initially it is almost linear, and then after saturation it is constant. But now if we move to higher gate voltage, if we use a different supply, higher supply, then I will have a much larger current because the channel will be stronger. Both the final magnitude of VDS and VGS will be much higher, right? So the current will be higher. So the current will linearly increase initially. At one point it will start saturation, it will enter into saturation, then it becomes constant. For another higher gate voltage, current will increase further, move much higher through my higher area, but it will gradually saturate and then becomes constant, right? And so on. So what we are observing from these ideal IV characteristics. What is an IV characteristics? IV characteristics is the mathematical or graphical relation between current and the terminal voltage of a MOSFET. And this is true for any electrical circuit. IV characteristics of any electrical circuit is the mathematical and graphical relation between voltage and the current, IV characteristics. So we are talking about IV characteristics of a MOSFET in graphical view in ideal condition. Initially they will linearly increase but gradually saturate. As soon as it enters into saturation, it becomes constant. But for NMOS transistor, what we are seeing here along this vertical line, from one VGS to next VGS to next VGS, the gap for the same amount of gate voltage increase is actually increasing, doubling almost. Why? Because of the quadratic relation, between drain current and the gate voltage in the saturation region. So the gap will jump from 1 to 0.5, 0.5 to 2, it is widening. So ideally, current ID in the saturation region becomes independent of VDS, but it will become quadratically dependent on VGS. It will jump from one to another. So this IV characteristics is showing dependence of ID on VDS for a certain gate voltage. Again, it is also showing the dependence of ID on different gate voltage for a certain drain voltage, right? So it is the complete ideal IV characteristics of MOSFET and MOS transistor. So now, if we want to summarize everything we have done for PMOS, in case of PMOS, body and source are tied together and it is connected to supply. In case of NMOS, body and the source are tied together and it is connected to drain. Before we move further, let me go back to one of these NMOS figure, NMOS figure we have. Yes. So, when NMOS and PMOS transistors are in operation, we have to follow certain convention to connect the terminals. In case of NMOS transistor, source is the lower voltage terminal, gate and the drain would be higher voltage terminal, because we have to apply a positive voltage here to form an N-type channel. We have to apply a positive voltage here to pull the electron out of the drain. So the source will be the reference ground, and gate and drain will be the positive terminal. But now we are saying that source and there will be a fourth terminal called bias terminal out of the body. They should be tied together and connected to the ground. In case of PMOS, gate has to be negative, drain has to be negative so that it can pull the positive pole out. Source is positive. Source and the body will be tied together and connected to the supply. So in case of NMOS and PMOS, source and body are tied together. In case of NMOS, source and body tied together, connected to ground. In case of PMOS, source and body are connected together, tied to supply. So what is the conclusion? Source and body terminals during the operation must be at the same potential. In case of NMOS, it is ground. In case of PMOS, it is supply. The question is why source and the body should be connected to the same terminal. The answer is we want to maintain a zero bias or reverse bias here, the PN junction between source and the body, because the electron is going out of this way, coming this way. If this PN junction disappears due to forward bias, then electron, instead of going the longer direction, it will start coming down, right? Because this PN junction barrier, by default that PN junction barrier will prevent electron from going downward or this way, only it will move through the channel. So to make sure that accidentally source and body PN junction here and here, they don't get accidentally forward bias, creating a short downward to the body, we always keep them in the same potential. If they are in the same potential, effectively there is no bias voltage applied, positive or negative, so they will remain at their default off condition. So those PN junction downward will not have an opportunity to turn on accidentally and derail the current. Instead of going from source to drain, it will come from source to body. That's why source and the body terminals of all the MOSFET transistors should be tied together to maintain effective zero bias across this PN junction, because our intention is to force the electron or hole from here to here. That's what will be useful to turn this on and off. If it goes this way, it is a leakage, right? We cannot use it if it is not coming out of the drain. Yes.
So in NMOS, the gate and the P is needed to be connected with the voltage.
Yeah, P is the body, so this is connected together. Connected to ground.
Okay.
So both remains at zero ground potential, same potential, no biasing here.
No biasing.
In case of PMOS, source and anti-body together tied to supply voltage VDD. So both of them remain at high potential. Effectively, the voltage difference is zero. Yes.
Are there any cases where you would want to bias the body differently from the source, like perhaps in an analog circuit application?
Oh yeah, actually even in digital application there will be, when we talk about noise control and the other thing, that's called body biasing. Sometimes we would intentionally reverse bias the body terminal to basically strengthen this barrier. So that ideally, if it's a zero bias, a barrier is there, no current will flow. But every device, no device is ideal, there is always a call diode reverse saturation current, leakage current. Only way we can weaken those leakage current if we can strengthen the barrier by reverse biasing it. So that's device engineering for specific operation noise control. So that's actually in the subthreshold region, how to apply those terminal voltage to control minimize or utilize those leakages, there is a group in Pardo, West Lafayette. For last 30 years, that's what they're doing. This entire group is all about leakage for ultra low power application. So, now let us look at this one. So in case of PMOS, the cutoff region will be when VSG, source gate voltage, is less than the magnitude of the threshold voltage. This PMOS transistor will be in off condition. For the linear region of PMOS, if VSG is greater than threshold voltage magnitude, but VSG is less than its threshold voltage, as you can see, I reverse the polarity, then it is a linear situation. A pinch of will occur when the source voltage becomes equal to saturation voltage, VSG minus VT magnitude, and it will enter into saturation when VSG greater than threshold voltage, and source drain voltage becomes equal to or greater than saturation voltage for PMOS. So the equation you should be able to write by yourself from this. This one will be mu P, this will be SG, this will be magnitude of VTP, this will be SG, this will be SG square, this will be mu N SG VTP magnitude square. So you just replace, yes.
I'm confused on the pinch-off condition versus the saturation voltage.
Okay.
Because when the saturation voltage implies is that it's now entering the saturation region, but the pinch-off implies that the channel is like closed off, like you don't have anything going across.
Okay. So when pinch of occurs, channel is not closed off. So let me then highlight. Thank you for asking. Even if you don't clear it, you will be in trouble. So pinch off is the beginning of saturation. So at the beginning, we have a, let's say this is drain, this is my source region. At the beginning, I have a continuous uniform channel, right? And then I applied a positive VDS here, so electron will start moving. As I increase this voltage, electrons will move much faster. So instead of having a uniform channel, initially I will have a tapered channel up onto source, right? And then if you further increase the voltage, the electron from the tip of the channel will move at a much faster rate than it can be refilled from here. So I will have a slightly shortened channel, so this area will not have any channel. So the moment the channel disappears, like pinch off, cut off from the tip of the drain, that's called pinch off condition. From that point onward, if you further increase, channel will become shorter and shorter, so this pinch off region will expand. So it will, the saturation region will start at the first appearance of pinch off channel. And as you further increase, because ultimately you are increasing VDS from 0 all the way up to VDD. Right? So now the question is, why as you are increasing your drain voltage in the pinch off region and it is spreading, why the current is not increasing? Because this region is now depleted from any channel. So any extra voltage or energy you apply will be needed to drag the electron from here to the drain region to complete the current path. So pinch off actually is the first point of the saturation. So it is the transition, the boundary between linear and the saturation region.
So that would be in the graph, that curvature would be the
you're exactly right. So
voltage.
where is the curve? Yes. So this is where actually pinch off occurring. So linearly increasing, the channel is reducing. At that point, channel will start disappearing. Because at that point, VDS becomes equal to VGS minus VT, which is saturation voltage. So when VGS is less than threshold voltage of 0, this is cut off. From here to here it is linear. This is pinch off. From there it is saturation. Yes.
And that would be why an NMOS would behave sort of like an inverter if you, it would be an inverter if you connected your output voltage from VDS. When you reach saturation region, then you've separated the drain from the ground. Whereas when you have the even channel through the whole system, the drain is already grounded essentially through that channel formation.
So, in that saturation region, the complete channel is not even there because
Right.
it's cut off from. So that's why that in that gap region, the current conduction will not take place like a regular metallic conductor. It will be a tunneling kind of mechanism. So at this point, we are kind of intentionally excluding those complex discussions. How actually that tunneling phenomena takes place in this small pinched of area. So, and as I said, there are a lot more physics to understand, just to understand the behavior of electron flow through that tiny tip of the channel region. So, but the other question is, in general, these MOSFET transistors, any MOSFET transistor is acting as an inverter. All the CMOS logic by default is called inverting logic. Why? You are applying a positive voltage to get a negative current of electron. You are applying a negative voltage to turn on a PMOS transistor to get a positive current. So you apply 1 at the gate, you get a negative current out of the drain for NMOS, which is 0 logic. You apply a 0 at the gate of the PMOS transistor, you are getting a positive whole flow out of the drain, which is a positive signal, which is high signal. So by default, all the CMOS circuits are inverting in logic because they are using NMOS and PMOS. NMOS for producing binary 0, PMOS for producing binary 1. But to produce that binary 0 in NMOS, you are applying what?
Voltage.
High voltage at the gate, which is 1. To produce a binary 1 out of PMOS, you are applying 0 voltage or binary 0 at the gate. So it's inverting by default. We will talk about more in detail as we move to CMOS behavior. But again, let me quickly give you some slide number. Slide number 19. Slide number 19 too. This slide number 36. This is a problem, but 35. I want each one of you to go through all the materials. If needed, I will repeat every slide again from 19 to 35. This set of slides will give you a very clear understanding of most ideal MOSFET behavior. If you can clear all the confusion about MOSFET behavior through these 17 or 18 slides, then you can handle any device behavior analysis. Thank you.